Okay, here is a quick review to Vogel equation. We have already gone through this example, which is fully saturated reservoirs, because this test point or stabilized point is below bubble point. Okay, here we have a test point of 200 stock tank barrel per day at PWF of 3000. Sorry, here this partial uh, partial saturated. Okay, we'll go back to the fully saturated one. Okay, so here for the fully saturated one, we have been given a reservoir pressure of 2085 psig and a stabilized point of flow rate of 282 at PWF of 1765, and the bubble point is 2100 psi. That means the reservoir is fully saturated because the reservoir pressure is less than oil point pressure. Okay, here we are requested to calculate the flow rate at zero well flowing pressure, which is maximum flow rate Qmax, and then to calculate flow rate at well flowing pressure of 1485, which is still below bubble point, as reservoir pressure is below bubble point. And then we are requested to calculate the bottom hole pressure necessary to obtain flow rate of 400 stock tank barrel per day. So here the reservoir is fully saturated. That means we only need to use Vogel equation as it is. Okay. Here are the answers. Okay. Last lectures, we have shown that how to calculate using Vogel equation. Just is direct substitution in the equation. We first substitute the test point, the flow rate versus PWF, and to get the maximum flow rate, we got maximum flow rate of 1097 stock tank barrel per day. Then we use this flow rate and introduce it into Vogel equation. Then we will get equation with two unknowns, PWF and flow rate. Then we can assume here we are requested to calculate the well flowing pressure, the flow rate at well flowing pressure of 1485. So by that we have a Vogel equation with three knowns, which is maximum flow rate, PWF, and reservoir pressure. Okay, then when we solve for flow rate, we get flow rate of 496 stock tank per day. And same for calculating the oil flowing pressure, we have been given the flow rate. Okay, so we can just solve for oil flowing PWF. Okay, we get PWF of 1680 SI. Okay, so for today we'll discuss how if we have only one test point above bubble point. That means we have undersaturated reservoir, but this reservoir is expected to be saturated when the reservoir reduced to below bubble point, or maybe the reservoir already became saturated, but we have no we have no current test point in the saturated range of pressure. We have, for example, all test point at pressure above bubble point. So in this case, we need to use both Darcy equation and Vogel equation. So we substitute the test point, which is for undersaturated region of pressure, to calculate J, productivity index, then we will use this J to calculate flow rate at bubble point. Okay, because bubble point is the end of the undersaturated region of pressures. Okay, so then we can use the flow rate at bubble point QB to solve for Vogel equation for the region of saturated pressures. Okay, so here are the steps. First, we need to calculate J using Darcy equation. J equals Q O over PR minus PWA. So PR we have already the reservoir pressure, which is the initial pressure should be above bubble point, and PWF are the test point values for flow rate and PWF. Then you can use this equation to calculate J. Then we use J, this calculated J to calculate QB, which is flow rate at bubble point pressure. Okay, and then we just use Vogel equation. Okay, so if you look at this form of Vogel equation, is same as the original Vogel equation, with exception that first we need to add the flow rate at bubble point QB, and then instead we use Qmax. We use the equivalent value of Qmax, which is J multiplied by PB, which is bubble point, divided by 1.8. Okay. So here, when we solve the two regions of pressure, we will get two curves. The first one is linear because it follows Darcy equation, so it will be linear from the reservoir initial pressure until bubble point. Then for the second curve, we use Vogel equation, modified version of Vogel equation to include the Qmax and QB. We will get a nonlinear curve like this. Okay, so we'll get one single curve, but this curve is combination of these two parts. The first part is for pressures above bubble point, that means for flow rates less than QB, which is bubble point flow rate. And the second segment is for saturated range of pressure, okay, where it is extended from QB to 0, okay, and for flow rates greater than QB. Okay, this an example. We have a reservoir average pressure of 4,000 and the bubble point is 2,000. That means the reservoir is originally undersaturated, and we have a stabilized point at of 200 at 3,000. That means the stabilized point is at pressure above bubble point. That means it is within the undersaturated range of pressures. Okay, so we need to generate IPR. So again here we although the reservoir or the data given indicates that the reservoir is undersaturated, but as our pressure should extend to 0, that means we have to consider what will be going when the reservoir drops or reservoir pressure drops below 2,000. Okay, so we follow this method. Okay, just first calculate J, then calculate QB, flow rate at bubble point. Then we use this equation to generate for saturated range of pressure. Okay, solution. Okay, above bubble point, J equals Q divided by PR minus PWF. So we have Q and PWF above bubble point. So then when we introduce the values, we get A equals to 0.2 Stockton barrel per day per PSI. Then the flow rate at bubble point, we use J value, this calculate in the first step to get QB of 400 stock tank barrel per. Then we have the modified Vogel equation. So in this Vogel equation we have two unknowns because QB we have already calculated, J already calculated, and reservoir pressure we have, and PB we don't need reservoir pressure, we need PB we have already. Okay, so we assume different values of PWF and calculate the corresponding flow rate. Then we'll come out with a table like this showing QO against PWF. Okay, so now you are requested, every student is requested to uh, 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 solve similar case like this one. Assume a reservoir of originally saturated, but the test point is the origin is undersaturated and the test point is given in the undersaturated range of reservoir. Okay, so we need to assume the reservoir original pressure is greater than bubble point, and to assume test point given between in the range between reservoir pressure and the bubble point, and follow the same procedure to solve the example. Okay, and thank you for watching this video.